This call is now being recorded.
Okay, let's go.
All right. Hi, guys, and sorry for the delay. Welcome back. We are now using Google Hangouts mainly because it has this raise hand feature, which I think will help us coordinate. So you are welcome to still write questions in the chat and so on, but the best way is probably to raise a hand. Then I hear a ping and I can address it. All right. So last time we talked about cyclic groups, and we have this notation. So G is a group, and you have an element lowercase g in the group G, and you can look at all the powers of this element. This is the set of all g to the n, where n is some integer, could be negative. Where I remind you that if n is negative, I mean g to the minus n is simply g to the minus 1 to the n. This is by definition. And this subset, this is a subset of G, of course, and this is in fact a subgroup. Moreover, if G is finite, then the subgroup generated by G can be written, in fact, as G to the n, where n is in the natural numbers. And in fact, this is going to be some finite set because G is finite. So it's going to be E, which is G to the 0, up to G to the K, where, or actually G to the K minus 1, let's say, where K is what is called the order of the element G. I mean, it's the minimal natural number such that G to the power of this number is again the unit element. Okay, and we saw an example, e.g., you take integers modulo 2 times integers modulo 3, and this is generated by the element 1, 1. I mean, if you add 1, 1 to itself, I mean, 6 times, you get 0, 0, which is the neutral element in this group. So this group is cyclic, and we had a proposition that says that if G is cyclic of order n, then G is isomorphic to the group of integers modulo n. Of course, the group of integers modulo n is cyclic because it is generated by 1. Right? You add 1 to itself, and times you get the 0 element. This is, if you think of it, this is kind of a classification, because it tells you that some notion that is abstractly defined as cyclic, at least in the finite case, is always of the form integers modulo n for some n. And we had a proposition that says that the number of generators, the number of distinct generators of Zn is what is called the Euler function phi n, which is all the numbers k smaller than n, such that GCD and k is 1. And this has an immediate implication if n is some prime p. Then any x in Zn, which is not 0, I should say Zp, is a generator. Okay, and so you can think of Zp as I mean, in ZP we use additive notation, so instead of g to the n I write ng, but it would be like e g 2g up to p minus 1 g, and you can do it for any g. Okay, and this gives you applications in cryptography, in fact. And when you use the additive group of integers modulo a prime, you can choose a basis, and this is you can call it the basis of logarithm, because the hard problem is to solve the so-called discrete logarithm problem. That is, I give you, I chose an element g as a generator, and now I give you an element x, so you know that x is equal to ng for some n. But I mean, to find n explicitly, if p is a large prime, to find n such that x is equal to ng is assumed to be a hard problem. Okay, and so what you can do, you can choose any g as a generator, and this will be the basis of your logarithm problem. So it gives you flexibility. Okay, so maybe in this context, it's worth mentioning small proposition, a subgroup of a cyclic group is cyclic. So suppose G is of order n. G is cyclic of order n. And take some subgroup H of G. If G is cyclic of order n, I can write G generated by some element lowercase g. And with this element G, I can express all the elements of H in particular, because I can express all the elements of G. So H is actually the unit element, which we can think of as G to the 0. And then you have G to the K1 up to G to the K D minus 1. So let's say the order of H is G. Is D. So what I'm doing here, I do not know that H is G to the 1 up to G to the D, because that's really not necessarily the case. But H must be H has D elements, so, and each of them must be a power of the generator. So I just named the powers K1 up to KD minus 1. Now, D is the order of H, it must divide N. So we can write N equals KD for some K. Now, since the order of H is D, if I take any element in the group H and raise it to the power of D, I have to get the neutral element. So G to the Ki to the D must be the unit element. This is, of course, G to the Ki D. This implies, in fact, it's equivalent to say that KID is some multiple of n some mi, right? Because that's the order of G. I mean, the order of G is n, because the whole group is generated by G. But then I have KID equals NMI. but n is kd. So this is kd mi. And now I can cancel out the d, and this gives me that ki is equal to k mi. Thus, each element in age is a power of g to the k. Right? Because I mean ki is k times m to the I, and ki is the power of the element g. I mean g to the ki. So I can simply write age as the unit element g to the k square, and so on up to g to the k d minus 1. Okay? And this of course means that age is generated by g to the k. Any questions about this proposition? Okay. So we saw that integers modulo 2 times integers modulo 3 is cyclic. But what is the general case? So the following lemma gives you a starting point. If G and H are groups, and G in G has order n, and H in H has order m. Then the order of this element G comma H is simply the least common multiplier of n and m. Okay, so this in the Cartesian product G times H. Yeah.
Sorry, Matan, can you remind me what GPS is? So you say if G and H are GPS, what does GPS mean?
This is my shortened writing for groups. So I say group like this.
Okay, fair enough. Okay.
Yeah.
Okay. Thank you.
Yeah, I will try to not use a lot of these shortings, but for some keywords,
No, it's fine. I was just taking notes and I got like
yeah.
I was so.
Okay, so how do we prove this? This is really simple. Say well, I take G comma H and I raise it to the nth power. In G times H, to do the operation is to simply do it coordinate wise. So to say that this is equivalent or this is equal to the neutral element is equivalent to say that G to the N is the neutral element in G, and H to the N is the neutral element in H. But this in turn is equivalent to say that the order of G divides N, and the order of G of H also divides N. So N must be a common multiple of N and M. And I remind you, the order of an element is the minimal number such that if you raise the element to this number, you get the neutral element. So if we see that this number needs to be a common multiple, it means that the order of GH is the least common multiple of N and M. Okay. Now, since we're dealing with the LCM and GCD, it's useful to know a small fact. Let's call it lemma. For two natural numbers, N and M, if you multiple the GCD of N and M and the LCM of N and M, you simply get N times M. Well, how do you see it? What we do here is we take a common decomposition into primes. So I write, for example, M equals P1 to the K1 up to PR to the KR, and N as P1 to the L1 up to PR to the LR, where the KI and the LI are bigger or equal to 0. So if I allow KI and LI to be also 0, this allows me to do the decomposition into primes over the same set of primes, because right you could have M equals P1 up to Pn, or sorry, P1 up to PS, and N equals Q1 up to Qt, and you have some powers here. I don't know, A1 up to AS, B1 up to BT, and these are not the same set of prime. So to get into this decomposition over the same set of primes, I simply allow the powers to be also 0, and then I can take all the list P1 up to PS union Q1 up to Qt, and I can express M and N over the same set of primes. But once I do it, I can express the GCD and the LCM in a uniform manner. That is, GCD of N and M is simply P1 to the maximum of K1 L1 up to PR to the maximum of KR LR. And the LCM is simply P1 to the minimum K1 L1 up to PR to the minimum KR LR. And from this, it follows immediately that GCD times LCM is N times M. Any questions about the dilemma?
No.
It should be LR. Okay, so what can we do with this lemma? This is the following corollary. Zn times Zm is cyclic if and only if GCD of N and M is equal to 1. And of course, in that case, you have Zn times Zm isomorphic to a cyclic group of order n times m. There's only one, so it's Z and M. So we have an if and only if here, right? So let's start with the direction of GCD and M equals to 1. Then the order of this element 1, 1, which we know to be LCM of N and M, is simply equal. I mean, LCM is equal to NM modulo GCD and M, but GCD and M is 1, so this whole quotient is NM. So we have an element of order n times m, which is the order of the group, right? Zn times Zm is of order n times m. So basically, it must generate the whole thing. Okay, so it is cyclic. Conversely, if GCD of n and m is bigger than 1, then the order of every element in Zn divides n, and the order of each element in Zm divides m. So for any element, the order of each element in Zn times Zm divides LCM of n and m. But LCM of n and m is by the identity we proved. This is nm modulo GCD nm, which is strictly smaller than nm. Because the GCD of nm is assumed to be bigger than 1. And this is a contradiction. So well, sorry, not a contradiction, but then Zn times Zm is not cyclic. Okay, so if we assume that the GCD is strictly bigger than 1, then all the elements have order strictly smaller than nm, and so the group cannot be cyclic. Any question about this proposition? Corollary? All right. So now maybe a famous corollary. This is called the Chinese Reminder Theorem. At least in a simple version. For nm natural with GCD equals to 1, maybe suppose then for all R and S, the system of equations X equals R modulo n, and X equals S modulo m as a unique solution. All right. Anybody has an idea how to build an argument for that? Well, I simply build an isomorphism. Well, for now, I define a function from integers modulo nm to the Cartesian product Zn times Zm. And this map takes x into x modulo n and x modulo m. Now, we actually saw that if you remember, we saw that if you map Znm into, for example, Zn, by taking x to x modulo m, you get a group homomorphism. And the group operation in the Cartesian product is done coordinate-wise. So this means that that F is also a homomorphism, because to be a homomorphism whose range is a Cartesian product is the same as to be a homomorphism to each component of the Cartesian product.
Okay.
Yes?
Can you rephrase this, or can you like go through this again? Because I had the intuition of using the isomorphism. That makes sense, but after you use it, I'm not sure how you map this Cartesian product into the other group, and that forms an homomorphism.
Well, okay. I mean, this you could simply multiply the two. I mean, if you give me 8ab, I can multiply.
Oh, I see. So you will get, okay, fair enough. You will get the same operation in both sides, and you can traverse both sides getting the same thing all the time. Okay, fair enough. Thank you. Sorry, could we also say that this application is bijective or not?
Yes. Okay,
I
just I mean, the first thing I wanted to address is that it's a group homomorphism, and I'm saying it's a group homomorphism because you have actually two maps here, Znm into Zn and Znm into Zm, and each of them separately is a homomorphism. This was an example we proved explicitly that each of these two is a homomorphism, and to be what I'm saying, to be a homomorphism into the Cartesian product, since the Cartesian product operation is defined coordinate-wise, to be a homomorphism into the Cartesian product is the same as to be a homomorphism into each of the components. So we know then F is a homomorphism. Okay, and now I claim that F is indeed bijective as well. Clearly, F of 1 is 1, 1, right? I mean, 1 modulo n and 1 modulo m. And since we assume that the GCD of n and m is 1, we know by previous lemma that the order of 1, 1 is n times m. So in fact, this already solves you the problem. I mean, you you map an element of order n times m into an element of order n times m. So you get everything, right? We get that f is bijective. Hence, it's an isomorphism. I mean, Zn m. Sorry. Now we are so this is if you want, the first part of the proof is telling you something we talked about. I mean, we knew that these two groups are isomorphic, but we didn't have a concrete isomorphism. And now that we have a concrete isomorphism, we can solve this system of equations. I mean, denote Rn to be R modulo n. And Sn to be, sorry, Sm to be S modulo m. And since f is bijective, the element Rn Sn in Zn times Zm has a unique source. X in integers modulo n times m, such that x modulo m equal to R, well, to Rn, and x modulo m equal to S brackets m. Okay, and that completes the proof. Any question about this result?
David is raising his hand. So.
Sorry?
David has the hand raised, so I presume he wants to ask something.
Yes, I wanted to, ask a doubt. So we defined concretely the f, so going from Cnm to Cn times Cm, or I don't know how to say. But the other way around, it's a little bit more tricky, right? Because what we put two lines down in parentheses, that's not the inverse of f, right?
Yeah, actually, I haven't thought about it. I think it's
because this, you can flip AB in many cases, and they will lead us to the same element. And
it could be. So you might be right. Let me delete it or put it in a question mark. The inverse, the inverse is. I need to think about it a bit. I think it, or at least intuitively, it looked like it should be A times B. But let's leave it for now. All I'm saying is to see that you have an isomorphism, you need to have a group map that is bijective. And to see that it is bijective, this yellow box it tells you everything, because you are mapping, I mean, the element 1 has order nm, right, in integers modulo nm. And the element 1, 1, by a result we prove, also has order n times m, because the GCD of n and m is 1. So if you map in an element of order n, of order k, into another element of order k between two cyclic groups, you have a bijective map, right? Because you are mapping, I mean, you have two cyclic groups. Let's say one is generated by G, and another is generated by H. So let's see, is G0 up to GK. And H is H0 up to HK. And you define a map by saying G goes to H, or if somebody gave you a map that in particular satisfies that G is mapped into H, then you know, and this map is a group homomorphism, then you know that this map must be bijective, right? Because it will map G square into H square and so on. Is this clear, David?
Yes, thanks. So, yeah, I'm fully convinced that it's bijective, but the thing is, at some point I had to try to go the other way around in a problem, and I remember it was a bit of a pain, I think. Can it be, so could you do f to the -1, so the other way around?
Yeah. So as I said, I need to think about it a bit, and I don't want to spend too much time. So maybe after the break. Okay. But yeah, it should be simple.
Okay, thanks.
Okay, so what I want to do now, I mean, soon we're going to take a break, but let me tell you a bit about the next steps. So this is usually referred to as classification of finite abelian groups. And what we mean by classification in mathematics is you take some kind of abstract object, like a finite abelian group, just a finite set with a binary operation and so on, and you give an exhaustive list of all the possible forms it can take. Of course, since since we're talking about any finite abelian group, this list needs to be some kind of rule that is applicative to any, to integers of any size. And we will see eventually, we actually saw the beginning of this classification result by by the proposition that told us that integers modulo n times m is in fact the Cartesian product of two of integers modulo n and integers modulo m in some cases. So the idea generally in this classification is to decompose a finite abelian group into a Cartesian product of simple groups, simple abelian groups. And we are now actually focusing on abelian groups. So it makes sense to change the notation. I write G with additive notation. And I write G plus H for the Cartesian product. Okay, this plus is coming from this convention. So instead of using multiplicative, we transfer into additive notation. And since we are leaving the kind of general realm of groups, I want to mention that indeed most of the results we proved so far were anyway about abelian groups, but we stated sometimes more general results, and this was kind of a deductive exercise to use the multiplicative notation instead of the additive ones, even when we talked about abelian groups. In fact, main results we proved, like Cauchy theorem and the first isomorphism theorem and Lagrange theorem, are actually true for non-abelian groups, but you need to formulate them slightly more carefully. And so now that this is done, we focus on abelian groups, which will anyway be the main application we have in elliptic curves. I guess now is a good time for a break, but any questions, remarks before that? Yeah.
Yeah, sorry. Could you just explain again on a previous part where you mentioned that the order of an element is n times m? I think it's above. Yeah, the blue ink.
Yeah. So what I'm saying here in the proof, we assume that that n and m are coprime. I mean, GCD of n and m is 1. And we had a previous proposition that said that in this case, Zn times Zm is cyclic.
Yep.
It's like, if you want, the simple example is what we did last time. Z2 times Z3 is generated by 1, 1.
Mm-hmm.
Okay. So if it is generated by 1, 1, then it means that the order of 1, 1 has sorry, I'm sorry for this. Okay, so this means that the order of n of 1, 1 has is simply n times m, right? It generates a group of size n times m.
Right. So order, the definition of order means, I thought it means the number of elements in a group, but in this case it's different.
So you need to there is a distinction. There is order of a group is the number of elements of a group, and there is order of an element in the group, which is the least integer or the minimal natural number, such that this element to the power of this number will become 1. I mean, O
right.
of G,
Okay.
O of G is the minimal n such that G to the n is 1.
Okay, got it.
Okay?
Yep, thanks.
And of course, in additive notation, it's the minimal n such that ng is equal to 0. Okay, and so I claim the previous claim we had tells you that the order of 1, 1 in Zn times Zm is n times m in case n and m are coprime.
Yep, thanks.
So now we have a map that maps an element of order n times m into another one of order n times m. It must be an isomorphism. Okay, so if there are no questions, I suggest we meet here at 10 minutes. Right. So the first thing we can do about the classifying a finite abelian group, well, we can generalize this this result we saw before the break. So we look at integers modulo n, and let n be p1 to n1 up to pk to nk. This I call the prime decomposition of n. So the ni's are strictly bigger than 0, right? They are. You have some list of primes to some list of powers, and you multiply all of them, you get the integers n, the integer n. Now, by the previous result, take let's say s is equal to p1 to the n1, and t is equal to the rest of it. So p2 to the n2 up to pk to the nk. Then, of course, GCD of S and T is 1, right? Because they do not have any common prime in there that divides them, and so they are coprime. And this means that integers modulo n is then isomorphic to integers modulo s, but s is p1 to the n1, times integers modulo t. And by applying the same argument on t, I get that this is isomorphic to integers modulo p1 to the n1 up to, or in fact, we are now in an abelian or additive notation, so I write this O plus integers modulo pk to the nk. Okay, so that's a nice factorization of integers modulo n. But of course, we are not guaranteed that every abelian group or every finite abelian group is integers modulo n. Of course, if the group is not cyclic, it cannot be isomorphic to integers modulo n. But we can do something similar. So for G finite. Actually, it doesn't have to be finite. Abelian group. And P a prime. We denote by GP the set of all elements in G whose order is, well, such that there exist, well, that O of A is a power of P. Okay, so it could be that A to the, I mean, this is equivalent to say that it's all the elements in G, and since we use additive notation, it means that P to the n A is equal to 0 for some n. But note that this n could be different for different elements A. I claim first that GP is a subgroup. So in our notation, this is going to be a subgroup of G. And why is that? It's very easy. I mean, if A and B are in G, so in GP, then, for example, P to the NA is 0. P to the M B is 0. So first, the inverse of B is minus B. And this means that P to the M minus B, which we know is equal to minus P to the M B, is again 0. So minus B belongs to GP as well. And A minus B, if you multiply it by P to the N, P to the M, you get 0 again. So altogether, A minus B, or A plus B as well, is also an element in GP. Okay, and GP is called the primary P subgroup of G. Now, we have the following lemma. Let G be an abelian group. And A, an element of finite order. Then I can write A as a sum, A1 plus AK, where the AI is our element in GPI with P1 up to pk, the primes appearing in the decomposition of the order of A. Okay, and these are distinct. All right. So how do we prove? We use induction on the number of distinct primes that divides elements of finite order in G. So we call this number K. So if K is equal to 1, we have only one prime that divides the order of the element A. That means that A is some prime power p to the t, let's say. But then, of course, by definition, A is in the p primary subgroup GP. So so that's okay. I mean, of course, it can be, then it is a sum of the form here. Now, suppose for every element whose order is divisible by at most k minus 1 primes, say p1 up to pk minus 1. Suppose that for every such element, I can write b equals b1 plus bk minus 1 with bi an element in gpi. If I now take an element such that the order of this element is divisible by k distinct primes, say the order of A is P1 to the N1. Sorry. Has to be consistent with the nodes. P1 to the R1 up to PK to the RK. Now I take M to be the tail of this decomposition. So P2 to the R2 up to PK to the RK. And N I take to be the head of this decomposition. So P1 to the R1. So of course, it means that I can write the order of A as simply N times M. And GCD of N and M is 1. Now, there is a lemma, I mean, a result from elementary number theory that says that if you have two integers who are coprime, like N and M here, there exist U and V in Z. I mean, they could be negative, such that UN plus VM is equal to 1. This is actually, I want it the other way. So MU plus NV is equal to 1. This is the so-called extended Euclidean or Euclidean algorithm. I mean, the Euclidean algorithm allows you to calculate the GCD of two integers. And the extended Euclidean algorithm finds coefficients U and V such that MU times NV is equal to 1. And using this, this is called, by the way, this is called Bezout. So U and V are called the Bezout coefficients. Okay, and so if I have these U and V, then since the order of A is N times M, and I remind you, N is P1 to the R1, I can write P1 to the R1 times M U A. Well, I should say first, these Bezout coefficients, I can multiply all this equation by A, and what I get is that MU A plus NVA is equal to A. This equation in blue is an equation of integers. But the equation here in purple is an equation of elements in G, right? So because G is written in additive notation, it means that I can multiply an element of G by an integer. So using this purple identity, what I have is that P1 to the R1 times MUA, which by definition is equal to NMUA. I mean, UA is an element in G, or if you want, A has order NM. So this is equal to 0. Which means that MUA is an element of G P1, right? Because I mean, if I multiply it by some, there is some power of the prime P1, such that if I multiply MUA by this power, I get 0. Also, I take M, and I multiply it by NVA. What I get is VMNA. But again, A is of order n times m. So this is 0. V times 0 is 0. So NVA, well, the order of NVA divides P2 to the R2 up to PK to the RK. So and now I can use the inductive hypothesis, because the order of NVA has at most k-1 distinct primes in its prime decomposition. So by inductive hypothesis, I can write NVA as a sum. Let's call it A2 up to AK, where the AIs are elements in the primary PI group. For I equals 2 up to K. But then we're done. Then remember, A is equal, we had this purple box. A is equal to MUA plus NVA. And MUA, we saw that it's an element of I mean, this is like MUA plus A2 AK, and you can simply denote this element is we saw that it's an element of GP1, so you can simply denote it as A1. Okay, and this finishes the proof. Any question about the lemma? So if you think of it, it's quite powerful, because it tells you that you take any finite abelian group. I mean, here in the lemma, it's not assumed to be finite, but for simplicity, I mean, since we only care about elements of finite order, we can assume G is finite. And then it tells you that you can express any element as a sum of elements, and each of these components of the sum are elements in primary P groups. And this lemma has an immediate corollary theorem. Let G be a finite abelian group with, let's say that the order of G has a primary decomposition as P1 to the R1 up to Pk to the Rk. Then I claim that G is isomorphic to the Cartesian product, or the so-called direct sum of all its P primary subgroups. So just before we get into the proof of this theorem, observe that each of these components of the direct sum is a subgroup of G. So we have kind of a funny case in which a big object G is isomorphic to the Cartesian product of some of its sub-objects. Before I go to the proof, any questions about the statement or the previous stuff?
I might have one, which is,
Yeah.
can we assume any properties for this subgroup in some sense that are forming G, in the sense of like they have to be cyclic if G is cyclic, but can we assume anything about their order, like the sum of the orders of the subgroups needs to end up being the order of G? Can we extract any extra properties from here that might be useful or not?
Well, I mean, what you can say is that, let's say we postpone the proof a bit. I mean, the order of GP is P to the n for some n. How do I know this? I mean, if there was another prime, I mean, if P prime would divide the order of GP, then by Cauchy theorem, I would have an element of order P prime. But GP, the definition of GP is all elements whose order is a power of P. So there cannot be any element of order P prime for another prime. So this means that the order of GP must be a power of P. But it does not need to be cyclic. Okay. Of course, it could be that GP is integers modulo P to the n, but that's not the only option. Okay. For example, it
What
could.
other option could we have?
What is another option? You could have integers modulo p times integers modulo p times integers modulo p to the n minus 2. Sorry for the here we use direct sum. Okay, and that's these two groups are not isomorphic because this group is cyclic, right? The upper one, let's say the blue one, is a cyclic group, and or if you want, here in this group, in the low, the purple one, you have an element 1, 0, 0, whose order is p, right? So you need to okay, you need to think a bit about it, but it's not going to be these two groups are not going to be isomorphic because you will have elements of different order in this I mean in these two groups, in the blue and the purple. So a priori we don't know what GP might be. I mean it could be I mean, we have a kind of a restricted range, but still there could be differences.
But how's that we cannot map now to the Cartesian product of ZP, ZP, and ZP? Sorry, ZP, ZP, and ZP to the n minus 2.
Well, we can map, but it's not necessarily going to be an isomorphism. I mean, remember that ZNM is isomorphic to Zn plus Zm if and only if n and m are coprime.
Okay, fair enough. Okay. I see.
Okay. So these two things are not going to be isomorphic. But what the theorem tells you is that whatever these primary P groups are, you can always decompose G into the direct sum of its primary P groups. Okay?
Okay.
So we take an element in G, and we know that the order of this element must divide the order of the group G. Hence, the primes in the decomposition of A are a subset of P1 up to Pk, right? These are the primes in the decomposition of the order of G. We can thus write A is equal to A1 plus AK with AI in G Pi. for I equals 1 up to k. And here, of course, it could be that, for example, P1 does not appear in the decomposition of A, but then we take A1 to be 0. Okay, so I can always do this. Claim that the sum in star is unique. Unique in that if I could write A as a different sum, B1 up to BK, with the BI being elements in the primary PI group, then each of the AIs would have to be equal to each of the BIs. So suppose that also A is equal to B1 plus BK. Of course, with the BI in the primary PI group. Then, well, I take these two equations, star and double star, and I conclude that A1 minus B1 is equal to B2 minus A2 plus BK minus AK. Now, this element, A1 minus B1, is a difference of two elements in GP1, and GP1 is a group. So this is an element in GP1. And similarly, here the direction is reversed, but it doesn't matter. It's still an element of GP2. And so on. This guy is an element of GPK. Okay, so if it's an element of GPI, it means there exists SI bigger or equal to 0, such that let's say BI minus AI is well, it has an order of PI to the SI. If we take M to be the tail of this decomposition, so P2 to the R2 up to PK to the RK. Actually, instead of R, I want S. So S2 up to PK to the SK. I mean, what does it mean that the order of BI minus AI is P to the I SI? It means that P to the I SI times BI minus AI is equal to 0. And for this choice of M, I get that M times BI minus AI is equal to 0 for every I between 2 and K. But by equation triangle, I get that M times A1 minus B1 also has to be 0. So the order of A1 minus B1 divides M, which I remind you is P2 to the S to the S2 up to PK to the SK. But this cannot be unless, but of course, this is an element of GP1. So its order has to be a prime, a power of P1. And P1, it does not appear in this decomposition. So the only way this can happen is that S1, so, right, we say, so if A1 minus B1, let's say as order P1 to the S1, then S1, the only way this can divide M is with S1 equal to 0. So A1 is actually equal to B1. And you do the similar argument to deduce, similarly, AI is going to be equal to BI for all I. Okay, we're almost done. So this is the heart of the argument. We now define F from G into the direct sum by I take an element A. It has a unique decomposition, A1 plus AK, and I map it into the elements A1 up to AK in all the tuple A1 up to AK. And uniqueness, so uniqueness of the sum says that F is injective. Right? Now F is surjective because if you give me any tuple, if you give me a tuple A1 up to AK, then I can construct the element A to be the sum of all these elements, of all the coordinates in the tuple. And by definition of f of A will be this tuple. So for every tuple in the target group, I have a source. And moreover, F is clearly a homomorphism. F is a homomorphism. I mean, if you take A, which you express as a sum, and B, which you express as another sum, then by definition, I mean, you know that A plus B is the sum of all these elements, and I can write it as A1 plus B1 plus AK plus BK. Now, since A1 and B1 are in GP1, so is the sum. This is true for all K. I mean, for all summons. So this means that the purple sum here is a decomposition of A plus B into a sum of elements in the primary groups. And we know that this decomposition is unique, so that's fine, and this means that f of A plus B is going to be equal to A1 plus B1 in the first coordinate and AK plus BK in the K coordinate. And this, by definition, is A1 up to AK plus B1 up to BK, which is simply f of A plus f of B. Okay, so we got an isomorphism. Any question about this theorem? Okay, so we are kind of halfway into the to proving the result of a classification, or sometimes it's called the structure theorem for a finite abelian group. For now, you can see that we are already able to decompose. This is the result here in blue. We are already able to decompose a finite abelian group into a direct sum of its primary P groups. And now the next step is to take a primary P group and to decompose it further. But this, I think it's better to postpone it for next time. Before we end, any questions, comments?
Just related to what you said now, these primary P groups that come from G, they don't need to have a prime order, right? Meaning they can also be decomposed.
Yeah, I mean, this is what is written here in this observation.
Yeah. I was Yeah. Because when you said primary, I went to like prime, but
Yeah, it's kind of it's primary because it's like a main component in the decomposition, but it's not a prime. Yeah.
Thank you.
Other questions? All right, so let's end here and see you next week.